Hi, good evening, everyone. Look at this topic. So, IUPAC from organic chemistry. Check it out. The basic things what we need to know is this. First, what are the allotropes of carbon? See, there are mainly three allotropes of carbon. One is diamond, graphite. The other one is fullerenes. Okay. Let me go one by one. So, when it comes to diamond, all the carbons in the diamond are sp3 hybridized. They are called as covalent solids. They are the hardest, they are electrically insulators, and they are very good conductors of heat. This is precisely used in thermometer. And if you compare the bond order, it is 1 and the bond length is around 1.54 Armstrong. So basically carbon having four different bonds like this, and this will keep on extending to the next carbons like this. All right, so it's a network of bonds like this. Okay. Next, if we talk about graphite, graphite is the most thermodynamically stable form of carbon. It has sp2 hybridized. All the carbons have sp2 hybridized with a single electron on it, which will showcase the delocalized pi bonds. It will have this hexagonal layered structure, while Cc bond length here is around 1.33 because of the double bond character, and bond length is 1.43, which is slightly more than double bond but less than single bond. Next, the distance between the two hexagonal layers is, held by weak van der Waals forces of attraction. One layer will slide over the other smoothly, thus it is used as a lubricant. It will have a high melting point. It is conductor in planes, as well as semiconductor across the planes. Used to make the electrodes in general, its thermal conductivity is less than diamond if you compare. Let's check out fullerenes. Fullerenes are sp2 hybridized carbons. They are hexagonal and pentagonal rings. They have similarities with the soccer ball. They will have alternative pi bonds with a bond order of 1.33. Molecular solid exists as C60, and the structure is called as truncated icosahedral. It is the purest form of carbon, and there are no residual forces or residual valencies left over here. Okay. We will be learning more in details about fullerenes as we visit, group 14 elements. So don't worry about more in details here. Graphene, it is a layer of graphite with only sp3 form. Bond order is 1.33. It is like the sheet of one graphite layer. Okay. Now, given any structure like this, you should be able to figure out what is the hybridization which is present on them. So do practice along with me. So this carbon is sp3 hybridized because it has four sigma bonds. Four sigma bonds. And what are the types of bonds? It is sp3 and s sigma overlapping. Okay. It has a tetrahedral geometry. Got it? As well as shape. Next. If you compare this carbon, second carbon, that is also the same thing. It is also sp3. You can see there are four sigma bonds on it. And it has two types of bonds. One is sp3 and sp3 sigma bond. The other one is sp3 and s sigma bond. Got it? The sp3 is here, and these are sp3 and s overlapping. Now, if you compare, it is also tetrahedral in structure. So this is also tetrahedral in structure here. Next, if you have a double bond, alpha is greater than beta in this case, right? Alpha is greater than beta, and the bond angle expected is around 109 degree. Sorry, here also I'll write down that 109 degrees 28 minutes. Here also we expect around 109 degrees 28 minutes. Here alpha is greater than beta. It is sp2 hybridized. It is trigonal planar in nature. Got it? The types of bonds, if you notice, it will have one sp2 sigma bond. You can take any one carbon. I'm talking about this carbon here. So it will show sp2 sigma bond as well as sp2s sigma bond. These are sigma bonds. And it will also show p pi and p pi bonding. It will show one p pi and p pi bonding. Similar logic here also. So here the bond angle is supposed to be 180 degrees. And it is sp hybridized. Any one carbon, if you compare, it is sp hybridized. It is linear in structure. The type of bonds include sp and s sigma bond as well as sp and sp sigma bond. Sp and sp sigma bond here. Got it? Let's see about the next one, which is C double bond O, and we have CH3 here like this. This is basically a ketone on which the carbon, if you compare the hybridization, here it is sp2. Okay, this is sp2 as well, and it has trigonal planar trigonal planar shape, correct? When it comes to oxygen also, it is hybridized. It is sp2 hybridized because of two lone pairs and one bond pair. Okay, got it. And usually you can feel that theta 1 is greater than theta 2. If you have a nitrogen here, you can make a note of it that nitrogen also will make sp hybridization if it is at the terminal with one lone pair and one uh, sigma bond. Okay. Next, if you have C3H4, these are called cumulines or allenes. Got it? What are the hybridization? Check it out. This carbon is sp2. This carbon is sp. This carbon is sp2 hybridized again. Got it? In cumulines, one very important thing you need to realize is that when it comes to this carbon, the pi bond which it is making here will be making a perpendicular pi bond here. So these two pi bonds will be always opposite, I mean perpendicular to each other. So you can see the pi bond plane is here, the other pi bond plane is here. So that's why these two hydrogens and these two hydrogens will not be on the same plane. Okay. So even number of pi bonds are always non-planar cumulines. Remember that. So 1 and 2. So 2 even number of pi bonds we have. So that means they are non-pair. But if you have odd number, like say 1, 2, 3, then first you will have this plane, then the next pi bond will be on this plane. Again, the pi bond will come onto the same plane. That's how we will have, planarity. So if you have odd number of pi bonds, they'll remain planar. Okay. Next, the question is about number of sigma and pi bonds in the following. Okay. This I would suggest all of you to do it, one or two. I will just write it down and check it out. See, in here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are all the sigma bonds. So sigma bonds are definitely 9 of them. And as you count the pi bond, also there are 9 of them. Got it? Likewise, if you can check it out how many sigma and pi in this case also. Number of sigma bonds we have 4. Pi bonds also we have 4. Here if you count the number of sigma bonds, please count and write on your own. Okay. 18, and here pi bonds will be 7. Got it? Now, given any of these structures, immediately try to figure out what is the hybridization on all the positions. See here, it is sp2. Here also it is sp2. This is sp3. sp3. Got it? And here it is sp3 as well, because one lone pair, 3 sigma bonds. Got it? Here you can see all are all carbons are sp2, and nitrogen is somewhere between sp2 and sp3. Why I'm saying that? Because it will always give resonance stabilization by the movement of lone pair. So lone pair is not localized there, it is not staying at its position. And these are amides. In amides it will be even worse. That means the delocalization is so strong that it will completely appear sp2. Okay, this will anyway be sp2, correct? This carbon is sp3, and oxygen here is again sp3, because it will always have the pi bond over on top of it, so that's why it will always exhibit sp3 form. Okay. So you can see this is that structure I'm talking about. This is how it exists. It is supposed to exist in this way, but the amide usually exists this way. Next, we have phenol. In phenol, this oxygen will be somewhere between sp2 to sp3. Otherwise, all carbons are sp2 hybridized. Got it? If only CH3 is present, this is called, carbocation. So wherever you have a carbon with a positive charge, we call it as carbocation. You can see it is maintaining the planarity here, so which makes the importance that it is sp2 hybridized. While CH3 here, it will be an sp3 carbon with pyramidal in shape. Pyramidal shape. Okay. If by chance there is any radical instead of negative charge or positive charge, if it is a radical, it will still remain sp2 and planar, correct? And this dot will be in the pure p orbital. Pure p orbital. Just keep that in mind. Okay, so we'll write this as simply CH3 dot. Right. Next, if you have CH2, this is called a carbene. In carbene, basically, carbon has an incomplete octet. So you can see only two bonds, one pair of electrons. So octet is not completed. It has only 6 electrons at any point of time. So that can exist both as two radicals in two pure orbitals. In that case, it is sp hybridized. Okay. And it will have slightly bent shape. It is not exactly linear. It will have slightly bent shape. In singlet, the lone pair will be a part of the orbital. So that means it will be sp2. Here also it will have a bent shape. Got it? Angles are slightly different, but I think that we will learn it when we discuss intermediates. This one is very important question, that is to find the number of atoms in the same plane. Got it? Maximum number of atoms. Okay. For example, I have written it here. You can see CH3C double bond Cn. This sp3 carbon is the only challenge, because it is sp3. One will be outside, one will go inside. The rest two atoms will be on the plane. So you can see these two bonds are on the plane. Then because it is on the plane, carbon is on the plane, and it is sp2 continued. So that will remain on the plane only. And this is sp continued. So this is all going to be in the same plane. So all these atoms will be on the same plane. So the answer is 6 atoms. Next, if you compare this molecule here, you can see 1, 2, 3, 4, 5, 6, up to this 7. Up to this, all of them are on the same plane. Correct. So from here, because all of them are sp2. But as it comes to this carbon, now it has become sp3. So one will be coming outside, one will be going inside. Then on this carbon, we will have OH, and one will be coming in, going inside, one will be coming outside like this. And wherever there is sp2, everything will remain on the same plane. So you can see all the hydrogens will remain on the same plane. So if we count all of them, total we have 17 atoms on the same plane, maximum 17 atoms on the same plane. Similarly, imagine I have a benzene, which I put it on this plane here, coming, out of the plane. And in that case, only on this carbon, which is sp3, there two hydrogens will go inside and outside. This hydrogen will remain on the same plane, correct? Rest all will remain on the same plane here. Check it out. Okay. So this way, if you count the total number of atoms, how many we have? 18 atoms. 18 atoms on the same plane. Lastly, here you can see again benzene. Benzene will always have all the atoms on the same plane here. Along with that, we have an sp3 carbon here. So one methyl will come out of the plane. Hydrogen will come out of the plane. Here, as you go across the end here, so this side here, we will have methyl's one carbon and one hydrogen will be on the same plane. The rest of the two hydrogens will not be on the same plane. Likewise, if you compare all of them, again I'll get total of 18. So total of 18. I would suggest you also first count, try to check geometrically you understood that or not, then write the numbers. Okay. Next, if it comes to bond parameters, generally bond length will be decreasing as the bond order is increasing. So I can say X is greater than Y is greater than Z. Bond energy wise, X is less than Y is less than Z. And if it comes to, number of, bond strength wise also, if you notice, 2X will be greater than Y when it comes to bond energy. Okay. 2X is greater than Y. Next, all single bonds, it represents it is sp3. If you have one double bond, it is sp2. If you have one triple bond, it is sp. Percentage S character is 25 here, 33.3 percentage here. Here it is 50 percentage. Bond length wise, if you notice, A is greater than B is greater than C. Bond energy wise, C is greater than B is greater than A. Correct? So I'm sure all of you are able to relate that. Okay. Next, when it comes to bond angle here, you would notice that delta will be greater than gamma. It is because of the crowding. You can see it is very bulkier groups here. So that will keep this angle as bigger as possible. Then delta, then we have beta, then we have alpha. Okay, in here we can clearly say alpha is greater than beta based on number of pi bonds. Next, here we can apply Bend's rule. More the fluorine will go away, percentage S character increases at the center. So you can see A is greater in terms of bond length, then B, then C, then D. This is the bond length form. When it comes to dipole moment, you know that HF will have more dipole than HCl, HBr, and HI. Okay. HF has extremely high polarity. Even though its distance factor is not dominant, the charge is very, very dominant factor. But when it comes to CH3Cl, slightly here it is changed. In this case, there is no, single chloride will have more dipole moment than multiple chlorides. If you have CH3OH and CH3N2, then CH3OH will have more dipole moment. And then if you compare ketonic form and, alkene, obviously here will have more dipole moment. And if you have fluorine here, I can say the magnitude wise ortho will always be greater than meta. Meta and the 1 will be same because at 120 degrees the magnitude will be matching. Thereafter we'll have para. Okay. These are some important dipole moments which you need to remember. Got it? So I think I forgot to write one more. I'll write it down here. You also make a copy of it. One is CH3Cl. If you compare with CH3F, CH3Br, and CH3I, this is an exception where we expect that the fluorine should be more, but the chlorine will be slightly dominant because of its distance factor. Okay, because it is charged into distance, so distance factor wise, chlorine will be slightly dominant. And next, when it comes to how many number of orbitals present, right, you can check it out. If you have number of sp3 bonding hybridized orbitals, you need to check out in C2H5OH. So write this structure and you notice that this carbon has sp3 of 4 orbitals like this. Okay, so we will have 1, 2, 3, and 4 like this. Okay, and then the oxygen, then the next carbon is also bonding here like this: 1, 2, 3, and 4. Okay, so let me rewrite that like this: 4. These are all 4 sp3 hybridized orbitals only. Then oxygen is making one bond here, one here, and then lone pair and lone pair here like this. Got it? So you can see that when it comes to hybridized orbital, how many number of hybridized orbitals which are present here, correct? Or sorry, we are talking about sp3, correct? So we can say that uh, hmm, and I'm only talking bonding hybridized orbital, not non-bonding. So in that case, Here all of them are bonded with hydrogen, all of them are bonded with hydrogen here, 1 2 3 here, 1 2 here, and 1 here. So these are all the hybridized orbitals. So if we count it now, you can say this carbon has 4 sp3 orbitals. This carbon has 4 sp3 orbitals, which are bonding kind, while this oxygen has only 2 sp2. Other two are sp3, and the other two are basically non-bonded orbitals. So in that case the answer would be 10. Correct. So we have 10 sp3 bonding hybridized orbitals, everybody. Okay. Now, let's understand what is formula analysis means. So basically, if you have organic compound with n number of carbons, then the maximum number of hydrogens that it can accommodate is 2n plus 2. That's when it forms an alkane, correct? So this is called Y max. And the presence of oxygen or sulfur will never change the relation here. So even if you have X or Z number of oxygens, the maximum number of hydrogens will always remain same. But if you have halogens, it is same as the presence of hydrogen. So it will replace the number of hydrogens. So here Y max will be equal to 2n plus 2 minus Z, because halogens are very, very similar to that of hydrogens. You have to remove that. While if you have nitrogen, you have to increase one hydrogen along. So that means Y max will be equal to 2n plus 2 plus Y. Y is the number of hydrogen atoms present. Okay. So sorry, not Y, I meant to say Z. So this will be Z. So this would be the number of maximum number of hydrogens we can have. Got it? Next, let us understand what is degree of unsaturation or double bond equivalent. It is also termed as index of hydrogen deficiency. If we have Cn and Hx, then index of hydrogen deficiency means you can take this as n plus 1 minus x by 2. Okay. So if IHD is 1, that means there existed double bond. Next, if IHD is 1, here you can see 4 carbons here. 4 carbons means how many number of double bonds or triple bonds we can have. Different way of writing the formula. You can write it this way: 4 plus 1 minus 8 by 2. Or you can then take a LCM here. So it is 5 minus 8 by 2, or 10 minus 8 by 2, which is 2 by 2, which is 1. So that's how index of hydrogen deficiency is 1. Okay. See, if it is 1 means basically I can make double bonds, right, across this C4 structure, or I can make one cyclic structure. Okay. These are the two forms which it can exhibit. Similarly, if you have C4H6, I'll get index of hydrogen deficiency or degree of unsaturation is 2, which means I can have 2 pi bonds or one triple bond. And one triple bond and pi bonds can keep moving around. Or I can also have one cyclic and one double bond, or I can have two cyclic. These are all the important forms. Okay, so let me write down that. If DOU is 2, correct, I can have I can have two double bonds. Okay, I can have two double bonds, or one double plus cycle, one cycle, one cyclic, or I can have one bicyclo, or I can have one triple bond. So these are all the possibilities which you can make. Okay. These possibilities help us predict the number of isomers. Okay. So it's better to learn that. For example, if you have C3H6O, degree of unsaturation is 1. So I have to keep on arranging double bonds and cyclic structures. So one double bond here, double bond here, double bond here. That this is one way. Or cyclo is one way. Or completely cyclic in this way. So these are all the ways we can represent. Got it? For 1 degree of unsaturation. Now, as a generic formula, suppose I have given Cx, Hy, Oz, Xp, Nq, Zr, like that, never ending as many number of groups you can have. Then how do we find out the degree of unsaturation? See, the formula is simple. If you have carbon X number, make sure you add 1 to it. Then subtract with as many Y atoms we have, as many P atoms we have, you add them and subtract as many nitrogen atoms we have. And that divided by 2. So remember, this is the generic formula. There is no role of number of oxygens and number of sulfurs present in it. Okay. So if you understand that logic, you can find out what is the degree of unsaturation here. Correct? For example, in this case here, you notice what is the degree of unsaturation here. So degree of unsaturation will be equal to 4 plus 1 minus 6 plus 2 divided by 2. Okay. So how much we are getting? 5 minus 4, which is 1. Similarly, if you compare here, C5H7N, so 6 minus 7 minus 1 by 2. Okay, so that is equal to 3. So which means degree of unsaturation is 3 for this compound. Okay, if at all I want to find out the degree of unsaturation only on the basis of structure, okay, either you write the formula like this. One thing is, whatever the structure you have, you count the number of carbons. You can see 1, 2, 3, 4, 5, 6. And because every carbon is double bonded, it cannot hold more than one hydrogen. So 1, 2, 3, 4, 5, 6. So there are 6 hydrogens. So this way you can count all the hydrogens, number of carbons, and then write down, then calculate the DOU. But if it becomes tedious, what you can do, simply check out what are all the logics that are fitting in here. So first is, you can see there are 3 cycles here. So I can say, first I have 3 pi bonds. That is 1. Then I have 3 rings. Correct? That's it. That 3 rings will make it 6. So total degree of unsaturation is 6. Got it? Second, another way of looking at it, suppose if at all I want to make this happen, so what I can do, see the trick here. So first you remove all the pi bonds. So how many you removed? 3. After removing that, you break a bond here and break a bond. First, I'll break one by one here. First here. Then after breaking this bond, one more bond is there. So let me break that bond also. So if I break that bond also, that means this is gone here, this is gone. Okay. But the cycle still is the same because the cycle is the same here. Correct. I will remove this part. I'll remove this part here. Correct. Now break this one more. So what are we getting after breaking that? Here I'll show it here. If you break it here, so that is gone. So now it has become open chain. So the objective should be simple. You have to make it as an open chain. So to make that open chain, how many times you have broken the bonds? So you can see first, if I take this structure here, the very first structure, if you compare what we did, we'll first break the pi bonds here. So 1, 2, 3. So 3 pi bonds were broken. After that, one more here, one more cyclic structure here, one more cyclic structure here. So total how many we broke? 7. Isn't it clear? So here also, if you break it here, if you break it here, 2, 3, 1, 2, done. So 1, 2, 3, 4, 5, 6. Sorry, not 7, 6. You can see 1, 2, 3, 4, 5, 6. So total 6 DOU. So that's what I have written it here. Clear? Same way, if you compare this compound, now you notice how many pi bonds we have. So count the pi bonds: 1, 2, 3, 4, 5, 6, 7. So total number of pi bonds we have is 7. Okay. Now how many rings are present? Only one ring is present. So plus one ring form. So that means degree of unsaturation is how much? 8. Got it? Next, coming to these coronine. In the case of coronine, how much pi bonds we have? Check out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So number of pi bonds are 13. So you break all the pi bonds here. Then check out how many rings we have. So just count directly the rings. That is mere the thing going to make more easily. 1, 2, 3, 5, 6, 7. Okay. This is 7 rings, correct? Now notice this one. After breaking all the 7 rings, the final ring will be the peripheral ring that will be left. So that peripheral ring you have to break. So that means you have to do one more. So total how much we have? 21. So degree of unsaturation in this case will be 21. So that is a coronium DOU. Prismane. Prismane is another structural form of benzene. So you can see this formula is the same. It is C6H6. C6H6, the degree of unsaturation is 4. You can do it as a formula or simply break the bonds here as well. So you can break here, here and here. Correct? Then only one big cycle will be left. You break that any one side here. So that makes it 4. Clear? This is cubane, C6H8. So I mean C8H8. So in this case, the degree of unsaturation will be equal to, how many we have here. So we can see, first I'll do it with the formula. So we will have 9 minus 8 by 2. Okay, so 5. I should be justifying this as 5. Correct? So I can use that as a concept here. Check out how many bond breakings are being done. So what I'll do, okay, I'll make this into unit and make it smaller. Okay, so that I can show the bonds, how they are broken. Yeah. Now check this out, how I'm breaking the bonds here. First I broke here. So imagine, so this is not there. Next, imagine after breaking that, I broke, this side also. So which means this front one is also not there. Okay. This front one is not there. This back one is anyway not there. Correct? These two are gone. So then I'm making one more breaking here. Let's say here. So if I break that also, in that case, you will not have this one, and this one. Okay. So I think they were combined form. I'll just open it up and keep it. Okay. Like this. I'll open it and keep it like this. Okay. So now you can see we have broken 1, 2, 3 bonds so far. Correct. Next, I can break this one. Now I can break here. So if I break that also, what do I get? You can see 1, 2, 3, and then 4. Okay, so this is the way it is present. Correct? Now this is what we have. Now you can see there is only one cycle left. This is the only cycle left here. So you break the cycle at any position here. Correct? So let me just delete this part. I'll copy this one only. So to delete that, I will use this bond. So as soon as you break this down, so that's it. Now you can see it has become an open chain. From here, like this, like this, like this, like this, like this, like this. So it is an open chain. So basically, how many cuts you made? So you can see 1, 2, 3, 4, 5. So 5 cuts we make. Hence, the degree of unsaturation is 5. This is another way of, expressing that. How much is the degree of unsaturation? Clear? Right. So this is about DOU, everybody. Now, let us understand what is the classification of organic compounds. See, organic compounds are classified majorly into two types. One is alicyclic, the other one is cyclic. Alicyclic, also known as the aliphatic form. So we can have, something like alkane, alkene, and all of that. Within cyclic, we can have two forms, homocyclic and heterocyclic. If a cycle is made up of all carbons, that is homocyclic. If any one of the nitrogen, oxygen like that is present, then that is heterocyclic. Okay. Next, you see in within homocyclic we have alicyclic also. Alicyclic means you have same carbon, all of them are carbon, but this does not lead to some special case. But there is one special case called aromatic, where the same ring will have three pi bonds inside. That will become aromatic. So homocyclic again will have two kinds. Everybody, it is alicyclic and aromatic. Within aromatic, we have two kinds of aromatic forms. One is benzenoid form, the other one is non-benzenoid form. Okay. So benzenoid form means all of them structure should be benzene, benzene looking kind. So you can see this is benzene, this is naphthalene, this is anthracene. All of them will have benzene form. Non-benzenoid means although they are aromatic, they are not they do not look like benzene. So this is a non-aromatic. This is a non-aromatic form. Why they are non-aromatic? Sorry, non-benzenoid. I'll explain you as we go ahead. But as of now, these are aromatic but non-benzenoid. In heterocyclic also again I'll have alicyclic and aromatic. Alicyclic is without any special case like aromatic. Here you have again special case. We can have one, two, three pi bonds. Here also in nitrogen we have a lone pair, so that makes it three pi bonds here. One, two, three. So this is also aromatic in nature. Okay, clear? Thereafter, when it comes to organic compounds, they can be categorized into two forms. One is saturated organic compounds, the other one is unsaturated organic compounds. Okay, saturated are the ones where they are not ready to accept any H2 molecule. Correct. So obviously here this will accept. So I'll have to delete that part OH here. So you can have sorry OCH3 here. So which means anything like ether. So ether also have single bonds. Alkenes will have, alcohols will have, amines will have. Well, benzene is actually, with three double bonds, but those double bonds will not add up H2. That's why even if you have a benzene form, you consider them as saturated. Okay. Unsaturated means typically if you have on a straight chain, you have double bonds or triple bonds, then that is unsaturated form. Clear? So these are all unsaturated forms. Now, notice this compound here. Let us quickly understand. This is all made up of carbons. So this is cyclic, homocyclic. It is alicyclic because this is not a part of some aromatic form and it is unsaturated. Now you can see this is cyclic. It is homocyclic. It is aromatic as well. Correct? It is benzenoid as well because it looks benzenoid, and it is unsaturated because outside there is a double bond. No, it is not because of the inside pi bond, but because of the outside pi bond, it is unsaturated. Okay. Next, if you have one double bond like this, then this is acyclic. It is unsaturated. If you have like this is also aliphatic and saturated. Okay. Sorry, my mistake here. So this is unsaturated, saturated. Next, again you can see this is cyclic, homocyclic, alicyclic, unsaturated form. Okay. So given any structure, I think you should be able to figure out whether they are saturated or unsaturated forms. Clear? Right. Now notice, generally how do we represent the organic compounds? The first one is called bond line structure. So you can see if we start only with single, if you have lines with, turns like this. So wherever there is a turning or wherever there is a starting point, it is always carbon. So you can see carbon, 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 and carbon. So that's how you write it down. And then satisfy their valency because carbons must have four bonds. So that's why you write terminals. We can write three hydrogens. Then the one which is in the middle is H2, 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 and last one is CH3. Okay, correct. Next, see. This is another way of writing benzene, which means there are six carbons and six hydrogens. Okay. So here, if you have it been given this way also, you know that these are all carbons. See, in triple bond, usually we get confused. This will go straight line. But wherever there is a double bond and double bond, total triple bond given, that means there is one carbon here where it cannot get a turn because of sp carbon. Even in the representation, the real representation also, we do not usually show turns. Okay, we'll take it as a straight line. Next, in case of functional group are present, then they must be written like this. Suppose if there is a functional group present, so whatever be the number of hydrogens present on it, you have to express all of them in a functional group. So this is the correct representation of a functional group form. This is a correct representation. This is a correct representation. Ketone, this one. cyanide. If you have an amine also, you can write it as NH2. If you have amide also, you have to write this as N double bond OR2 like this. This is an amide. So you have to always show anything other than carbon, right? If at all it is present, and on top of that, if it may have hydrogen, you have to represent all of them and show it. Okay. So this is called bond line structure. The next one is the condensed form here. You can see when it comes to condensed form, basically the same bond line here, you're just trying to condense it without showing the bonds. So without showing the bonds, if I just show the dots, or even if I don't show the dots, that is called as condensed form. But in the condensed form, important point is you need to represent how many hydrogens each are carrying. Okay. Next is semi-condensed form. Semi-condensed form is when you have, bond between carbons represented. It is the same condensed form, but bonds between carbons should be always represented. Next, this one, if you notice CH3 here connected to this carbon, then there is a double bond between these two, then there is a double bond between these two, then carbon, and that has two CH3 and CH3 group. So this is how you can write it down. So this is a condensed form, and we are showing it how the bond line form will look like. First, these are with carbons. Now the actual bond line form should be without any carbon. So this is the correct structure. In case of any functional group like this, you have to represent everything like this. Okay. The terminals is not necessary, but it is easier when you have only one carbon on the terminal, better to represent. So this is the anhydride form. Next is structural formula. Structural formula is writing every bond that is available. So if you have N-butane, write every bond that is possible, then that is a structural formula. Okay. Next one is molecular formula. That is the most concise way of representing the number of carbons and hydrogens. Okay. Next one is empirical formula. That means you take out the common amount here and make a simplest ratio. The simplest ratio is 2 is to 5. Okay. Wedge and dash representation. Suppose if you have methane, methane is tetrahedral. In tetrahedral, one hydrogen will come out of the plane, and this particular form where we call it as a dash wedge, that will go inside the plane. So dash is going inside the plane, solid which is coming outside the plane. Got it? These are all the representations. Next, let us understand what are the types of carbons and hydrogens are generally present. Okay. So usually if you notice what are the types of carbons and hydrogens present, check it out. If you have a carbon which is connected to one more carbon, then that particular carbon will become 1 degree. If this carbon is also connected to one more carbon, it is going to be 1 degree. If it is connected on the hydrogen, if 1 degree carbon has a hydrogen on it, then that is called as 1 degree hydrogen itself. So this carbon is read as primary carbon, and this hydrogen is read as primary hydrogen. Got it? That's how it will be. Primary hydrogen and primary carbon. Next, you notice this molecule here. So we have 1, 2, 3, 4, 5, 6. All of these are carbons. Here also there are carbons. All terminals are also carbons here. So now notice this one. Everything which is this carbon has only one carbon connected. This also has one carbon connected. This also has one carbon connected. So terminals were always called as 1 degree or primary carbons. So you can see there are 6 primary carbons here. Second, if you have 2 degree carbons, you can see one here and that's it. There is the only one we have. 3 degree. If it is 3 degree, you can see these two are 3 degrees. So two of them. Next, we have 4 degree. 4 degree will be, uh, this does not have any hydrogen. You can see only carbons are there, but no hydrogens on it. So I hope all of you got the list of carbons. On the same lines, I want you to just take a minute and try it out how many number of 1 degree hydrogens, 2 degree hydrogens, and 3 degree hydrogens are present. Okay, so you can pause it and do it once and then check it out. Okay, check. Here it is 1 degree, 1 degree, 1 degree, 1 degree, 1 degree, and 1 degree. So total these many number of carbons we have, and each carbon will take three hydrogens on it. So total 18 1 degree hydrogens, and then you can see 2 degree here, and that's it. Only one of them is 2 degree. So since it is only one here, so one into two, because 2 degree will have two hydrogens on it. Next 3 degree. 3 degree will have only one hydrogen, so one here and one here. So total we have two. Okay, so that is two. So this is about number of hydrogens. Okay, I want you to take some time out and do these questions. Pause the video, try it out, and then check out and match with the options. Okay. See what I am getting. 1 degree carbons, I'm getting it as 6. 2 degree carbons, I'm getting it as 5. 3 degrees, I'm getting it as 6. 4 degrees, I'm getting it as 1. Check with your answers. 1 degree hydrogens, I'm getting as 18. 2 degree hydrogens, I'm getting as 9. 3 degree, I'm getting it as 1. Okay. Then in this case, this is very important case, guys, because the suddenly when it comes to sulfur, oxygen, nitrogen, then carbon here, for example, let me elaborate this carbon. This carbon is connected to one more carbon, but here it is not connected to one more carbon. It is connected to sulfur. So this, I will still take it as 1 degree only. So it is 1 degree. Here, this is 3 degree definitely. Now, same is the case here. This is 2 degree carbon. Okay. So here also, this is 1 degree carbon. Although it is connected to two oxygens and one carbon, it is still considered as 1 degree carbon. Okay. So here you can see again it is 2 degree carbon. Here we have 2 degree carbon. Here also we have 2 degree carbon. Here also we have 2 degree carbon. Right. Here, here we have 1 degree carbon. And here also we have 1 degree carbon. So here we have 3 degree, 1 degree, and 1 degree. These are all the parts we have. And finally here we have 1 degree only. Right. Putting that into the picture, now you'll notice that how many number of carbons, hydrogens, and everything is present. So check out 1 degree hydrogens. If you figure it out here, we will get I think 18. Okay, clear? So 1 degree carbons, how many we can have? See, 1, 2, 3, 4, 5, 6, 7. Okay. Oh, I think we got 7. My mistake. Right. Seven we have, but how many hydrogens we have? Because not all of them is like 7 into 3, and that is 21. It will not happen like that. So you need to check out how many number of hydrogens we have present on it. So I think that itself is coming out as 18. Similarly, when it comes to 2 degree, we have got 9 of it. 3 degree, we got only 1 of it. Okay. Right. Sorry, I'm talking about the hydrogens. Right, everybody? That is one classification. The next classification is about allyl, vinyl, phenyl, benzyl positions. Simple, you see, any sp2 carbon which is present not on a benzene ring, other than benzene ring, wherever there is an sp2 carbon, we call it as vinylic carbon. So this is sp2, sp2. So what is this one? Vinylic. The next carbon which is connected to the vinylic, which has to be sp3 carbon, that is called as allylic. So C adjacent to vinylic, so that makes it allylic. Next, every carbon on benzene is sp2 hybridized here. Okay. Next, this carbon. Acha, everything which is sp2 hybridized here, that is called as phenylic carbon. These are all phenylic carbons. Now here all six are phenylic carbons, and one carbon which is present on top of it, that will be sp3 hybridized, that is benzylic carbon. So from phenylic it has become benzylic carbon. This is something very important to understand, that allylic and benzylic can only be viewed when it is sp3 carbon connected directly to sp2 carbon. Okay. So let's see. Take a pause and check out this question. For this question, you need to find out how many vinylic, allylic, phenylic, benzylic carbons and hydrogens you have. And listen, whenever there is a phenylic group present, then you do not consider it simultaneously as vinylic. And whenever there is benzyl present, simultaneously don't consider it as allyl. Okay. So using this concept, you can see now when it comes to uh, carbons, number of vinylic carbons are 4. Let me show you where. 1, 2, 3, 4. These 4 are vinylic. Next, allylic. Allylic is only one. That is this one. This is the only one which is allylic. Got it? You can say, sir, this one is also allylic. But this is benzylic as well. And since benzylic is there, you do not consider it as allylic anymore. Next, phenylic. Phenylic means everything present on the phenyl. So that means it is 6. Number of benzene, benzylic. Benzylic, how many we have? Check it out. This is benzylic, benzylic, and benzylic. So 3 benzylic carbon positions we have. 3. This is a number of carbons. If it comes to hydrogens, you will read this, you will get it as 6, 2, 3, and 4. These are number of carbons and number of hydrogens. Okay. Right. Next. Check out how do we assign the degree of compounds, like 1 degree, 2 degree, 3 degree of a functional group. Suppose if you have an alcohol at the carbon which is 1 degree, then you call it as 1 degree alcohol. If the carbon is 2 degree, then you will call it as 2 degree alcohol. Similarly, it is 1 degree amine, 2 degree amine, 3 degree amine. Okay. Sorry. This is carbon is 2 degree, clear, but the nitrogen still is connected to, only one carbon, correct? So you have to check with respect to nitrogen. Nitrogen is connected to one carbon here. Here also it is one carbon. Here also it is connected to one carbon. Hence, this is 1 degree, this is 1 degree, and this is also 1 degree. 2 degree is when you have two carbons connected to nitrogen. So then it is two carbon connections. So it is 2 degree amines. If you have 3 carbon connections, you call it as 3 degree amines. Clear on that? So this is about 3 degree amines. Next. Check out the same logic for halogens also. If chlorine is connected to the 1 degree carbon, it is, 1 degree chloride. If it is connected to 2, it is called 2 degree chloride. Okay. It's called 2 degree chloride and so on. Okay. And next, see, we learned one thing, that hydrocarbons are of two kinds. One is saturated kind and unsaturated kind. Saturated kinds are, industrially called as paraffins. Unsaturated ones are called as olefins. And, olefins are usually alkenes. And then we also have alkynes. Alkynes formula is known. CH, Cn, H2n minus 2. Here it is Cn, H2n, and here 2n plus 2. Saturated hydrocarbon does not mean it does not have this form. Correct? Here this is saturated as well. This one is also saturated. Saturated in the sense this does not take H2. So if you have a ketone or a aldehyde, it is very debatable. Does it take H2 or not? This usually does not take H2. That's why it is called as saturated. But while counting, we usually count it as, unsaturated form, because counting of degree of unsaturation is always theoretical. Okay. So this is saturated kind. This is saturated kind. Unsaturated is when you have a double bond form like this. These are all generally unsaturated forms. Okay. Right. Next, what are the prefixes used? That means when this group is connected from a certain position, what do we call it? If it is connected from this carbon to some, let's say, main chain, then this will become benzylic. If it is connected directly to phenyl carbon, then it is called as phenylic. So you can see this is benzyl alcohol. This is also benzyl fluoride. Okay. Suppose if the carbon already has two chlorines in it, instead of xyl, that is benzyl, you call it as benzar. Okay. You use the word al. Instead of il, you use the word al. So it is actually benzyl chloride, but you see in NCRT, they also use the same term as like this, benzyl dichloride. Actually, this is not right. Okay, di is not necessary because the al itself represent there must be two chlorines, but it is already given. So I would suggest you to accept this way also. If it is dichloride is been said, you can still accept it. Same way I have written the next one also. You can see this is this carbon having three chlorines here. Then we call it as benzo. Okay, just like benzoic acid, correct? Because if the valence is three, we write it as benzo. So this is benzo chloride or benzo trichloride. Benzo chloride or benzo trichloride. Okay. So you can see if phenyl is a substitute on some group here, so there is a main chain here somewhere, and phenyl got substituted there. So then we simply call it as phenyl. And within the phenyl, you can see C6H5, pH, AR, and sigma. These are all the forms which you need to understand. Clear? All of them are phenylic forms. If there is a methyl group on top of the phenyl, then we call it as toluene. Correct? Then we call it as toluene form. In such cases, what do we call the others here? Correct. So if you have any pH here, so we can call it as phenyl present on which one? Second position, and this is butane. Clear? Similarly, here also it is the one and same here. So if you have three sigma bonds, so that is going to be trityl. This is called as trityl chloride. Trityl chloride. Okay. Next. If by chance you have a connection from oxygen on this end, this is called O-phenylic group or ortho. Next. If you have like this is going to be metaphenyl groups here. So if by chance you have methyl here connected with one more methyl, you call it as tosyl. If you have methyl present on benzene here and connection is from this end, then it is called as tosyl. Metatosyl. This is paratosyl. So remember, O is for ortho, M is for meta, P is for para. Lastly, O-tosyl chloride. This is M-tosyl bromide. So these are the forms we have. So trityl is always this representation. See, wherever I'm using this one, correct, which is xy, is same as saying that as, you know, uh, this way. Okay. Next. Acetylyl carbon means what? So if you have acetylene, this one, if it is directly connected to some, you know, main chain in this case, then this compound is called as acetyl group. Acetyl groups. Okay. So you can see CH triple bond C, CH2OH. So this is going to be uh, acetyl ethanol. Okay, clear? Or we can use this as another name like this. So if you have CH3, C triple bond CH. Now, or from this carbon, if it is connected, that is called propargyl alcohol. So this entire part is called propargyl. So this will become propargyl alcohol. Correct? Next, check out type of groups in the saturated hydrocarbon. If this is a principal chain and there are different groups on it, then R1 and R2, these are called substitutes, are the branches. And since they are branches, you will again have to have, one hydrogen removed to make it as yle. So this will become methyl. If you have this one ethyl. So it is methyl, ethyl, propyl, butane, pentane, hexane, heptane, octane, nonane, decane, undecane. 11 is undecane, dodecane. Then we have ICOS. So this is about C20. Clear? So whenever you put it as a substitute, you first write the word number. This is called word name, which is myth, and it is an I. So that's why it is called methyl. So this one will be ethyl. Right, everyone? I hope all of you got this point. Right. See, notice this one. If alkyl, R is the alkyl, if connectivity carbon is always sp3, that connectivity carbon should always be sp3. So you can see this is ethyl. This is single carbon methyl. This is isopropyl. Okay. You can use the word isopropyl or you can simply write it as methyl ethyl. Okay. So this is methyl ethyl form. Got it? Next. Notice if you have the names like iso, neo, secondary, tertiary, these are the types of uh, types of names that have been used. Check. First one, if you have four carbons connected to a main chain, this will become butyl. If you have four carbons like this, it is isobutyl. This is pentyl. This one is isopentyl. Next we have uh, secondary butyl here. So we can call it as 2-degree butyl. Here it is 2-degree pentyl, and it is secondary propyl, or you can also call it as isopropyl in this case. Last, if you have this group decided, it is called tertiary alcohol. Sorry, tertiary butyl form. Sorry. Next, this is tertiary with a pentyl form. One more methyl extra on it. Got it? So if I keep pushing the pentane here, so you will get this form here. Carbon with three methyl groups on it. So that will become neopentyl. All right. So just go through the connections once quickly, then we can go ahead. The common names. If you have a straight chain, you usually call N-pentane, N-hexane, neopentane, tert-butane, isopentane, isohexane, and neohexane. These are all the various forms you can name it. So quickly watching that, you have to write the common names of the compounds here. All right. So I'll write one or two. Rest you can do it now. Okay. The first one you can see, I can call it as neopentyl form, isn't it? So that's why it is neopentyl alcohol. It is an alcohol form. Next. Now the minute other than primary position it is called coming across, we call it as active. So now we call it as active secondary pentyl. Secondary pentyl alcohol. Third one. Third one, same thing here. This is also neopentyl amine. Next, this one. Here we have, secondary pentyl alcohol because it is a secondary position. So we can call it a secondary pentyl, right? So we have this as secondary pentyl alcohol. Done? Right, check it out. Next one. If you have an amine like this is going to be tert pentyl, tert pentyl amine. What about the next one? This will become secondary propyl bromide. Next. Here we have this as isopentyl amine. Isopentyl amine. Okay, or this is going to be isoamyl amine. Next, here we'll get this as isopentyl. Done. So this is going to be isopentyl alcohol. Another way of writing it is isoamyl. Amyl is always used for 5 carbons. So then it is isoamyl alcohols. Right? Isoamyl alcohols. Got it? Right. Okay, guys, the next part is all about unsaturated substitutions. So that means single bond is connected, double bond is the next carbon is not sp3, it is sp2, but connected with a single bonded with uh, main chain. So then it is basically a vinyl group connected. So that's why we call it as vinyl substituted, or it is ethene with an ene with a yl. So that's why it is read as ethenyl. So this is propenyl. So this is allyl. Okay. So prop 2 in YR, 1 I. So that is how we write it down. Similarly, last one, if you notice, so this is going to be iso. Okay. Sorry. So here, notice that. So we have ethene, yl, ethenyl. This is how it is been written. So you can see same way. What could be a name here? This will be butene. Second position, we have ene. This is an ine because it is alkyne. Then yl. So that is butane, 2-ine, yl. Third one, this is going to be 3 carbons. So this is propynyl. Next one, if double bond is directly connected on that, okay, by chance if double bond is directly connected, then the methene, the single carbon is called as methylidene. And if you have 2 carbons, you call it as ethylidene. Ethylidene. If you have it like this, we call it as isopropyl. Okay, so isopropylidene. So that is isopropylene. Done. That's it. This is the basic introduction towards the IUPAC. If you understand all these terms, then the naming of IUPAC becomes very easy for us. Got it? So this much work I expect all of you to complete that and keep it. Got it? So as we go to the next session, then we'll discuss all the IUPAC at once. Okay. Thank you.